All right, so I want to start talking about Lewis structures and bonding proper. So ionic compounds had been reasonably well understood for a while. We kind of knew what the magic number of electrons were for certain elements, and that told us why certain elements adopted the charge that they did. We learned this way back at the beginning of the semester, so we know that everything in the first group, like sodium, lithium, potassium, they all have one more than a magic number of electrons, which is why they make +1 ions. Fluorine, chlorine, and bromine are one short of those magic numbers that the noble gases have, and that's why they form exclusively -1 ions. Now, it turned out to be a problem that a lot of compounds, the empirical and molecular formulas for a lot of compounds were not easily explained by that formalism, and most importantly, carbon-containing compounds were not easily explained by this. And you and I are made up pretty much of all sorts of carbon-containing compounds, so this is a problem. So in 1916, Gilbert Lewis had this idea that maybe electrons weren't necessarily transferred. So previously, they thought everything was ionic. And he said maybe electrons would lose or gain to share to hit this magic number of 8. So that's why we call them octet rules. And based on the formulas of a lot of what we now call covalent compounds that were known back then, 8 did seem to be a magic number. Now, we will learn that it is not the only magic number, but thankfully for him, it was based on the information they had there. 8 was the one magic number. Otherwise, I think we might have had a hard time seeing what the pattern was. And the idea was that in this case, complete electron transfer just did not adequately explain the bonding. And so he thought, okay, maybe everything just doesn't, maybe it's not all electron transfer, maybe they just share. And the other great insight that he had was that the electrons were shared pairwise. And then they would share these electrons to achieve noble gas valence configuration. So again, the magic numbers, or that we now know, the completely filled shells that the noble gases have. So let's talk a little bit about how this works. But first, we need to talk about more specifically the idea of these valence electrons. Now, we talked about this a little bit when we talked about electron configurations. They are basically the outer electrons, but we have to invoke a more precise definition right now, and then we can go on. All right, so valence electrons. They are simply, so they are the outermost electrons. They are the ones that are shared. So sharing occurs when the spatial extent, or if you will, the orbitals, actually physically overlap. Again, so these electrons are occupying space between the nuclei. And the ones that are the furthest out are the ones that do this. The inner more electrons, to get them in the same region of space, then the nuclei get way too close together. So it's the outer ones that are essentially felt by both atoms that you're trying to bond together. So they're going to be defined as all of the electrons in the highest N shell. And in addition to those, remember now N kind of gave us an idea of what the size of a particular type of electron was. So there are all the electrons in the highest N shell, and then any of them in a lower N subshell that isn't completely filled. And this is pretty much going to be d electrons in any of the examples that you see. So for example, the electron configuration of fluorine, 1s2, 2s2, 2p5. So the highest value of N in this case is 2. And you actually have 7 of them. So fluorine, the element fluorine, is said to have 7 valence electrons. So again, we've got 2 s-type electrons and 5 p-type electrons. Both have n equals 2, so there's a total of 7. Now, as far as that incompletely filled lower subshell, titanium is a good example of this. The electron configuration of titanium is an argon core, 4s2, 3d2. Now, the highest value of n in this configuration is 4. So those 2 4s electrons count. And this 3d subshell is not completely filled. It only has 2 electrons, and you could have as many as 10. So those electrons count. So titanium has a total of 4 valence electrons. The 2 4s electrons, and then the 2 3d electrons. And again, this lower n subshell incompletely filled, pretty much going to be d electrons. All right, so let's make some really simple molecules together. And again, because the 3p and the 3s subshells are completely filled, those electrons don't count as valence electrons. All right. So we did fluorine, so let's talk about fluorine. It is tradition, not quite sure why, to represent the valence electrons as pairs of dots, when applicable, around a particular symbol for the element, maybe as if they were, you can imagine a box, a square box around it. And you put pairs of them, and if you have an odd number, then you're going to have one that's not paired. And then we would have another one. And the rule is pretty simple. So each is 1 electron short of the octet, a magic number of 8. And the rule is just if you share one, you get one. So let's say that these two are shared between the 2 fluorine atoms, and then we switch the picture. And if these are shared between the 2, now each of these has a total of 8 valence electrons because shared ones count for both atoms. Now this is going to be important. So you get 1, 2, 3, 4, 5, 6, 7, 8, and you would have exactly the same picture for the other one. This we say is having a filled octet. And to make these structures a little easier to read, we typically represent a shared pair of electrons as a single line or a bar. And we call that a single bond. Or we'd also might call this a bond order of 1. And that's pretty much it. But let's do a few more. So let's step back 1 in the periodic table to oxygen. So oxygen actually has 6, and I guess I misspoke about this. If you're drawing these little dots, and we're not going to do them for very long, you pair up the first 2, and then just like Hund's rule, go 1, 2, 3, and then 4 if you have to pair it up. So oxygen has 6 valence electrons. You've got 2 2s electrons and 4 2p type electrons. So in this case, they're going to share 2 pairs. In this way, each oxygen atom will have sort of access to a total of 8 electrons. And we would draw it like this with 2 bars between the atoms, indicating that there's 2 pairs of electrons shared between these 2. And these here are referred to as unshared pairs or lone pairs. And if the 2 pairs are shared, that's referred to as either a double bond or a molecule that has a bond order of 2. So we can do one more like this, and that's nitrogen. So nitrogen has a total of 5 valence electrons. So 2 2s electrons and 3 2p electrons. And so it needs 3, it's going to get 3, or it needs 3, it'll share 3. So there are 3 shared pairs between these 2 atoms, and we draw that with 3 bars. By the way, if you're looking at the symbol font set, this is actually a defined as sign. In cases like this, we would say this is a triple bond, or something that has a bond order of 3. Now, we are going to learn we're going to be counting electrons 2 different ways in our quest to make molecules. The first way is what we've been doing here, namely that we count shared electrons for both atoms. So here, for this one, you would go 1, 2, 3, 4, 5, 6, 7, 8. And you do exactly the same thing for the other one. 1, 2, 3, 4, 5, 6, 7, 8. So the shared electrons count for both. All right, so this is octet counting. And let's go, we're going to do this again for this molecule here, CS. So CS has a triple bond between the carbon and the sulfur, and there's an unshared pair between both. And both of these can also be assigned to 8, so 1, 2, 3, 4, 5, 6, 7, 8, just like the N2 molecule. So each of these has what's called a full or a stable octet. It's got 1 unshared pair and then 3 shared pairs, giving you 4 pairs, which is 8. Sulfur gives you the exact same picture. Now, there's going to be another type of counting that we call formal charge counting. And in this case, you actually evenly split up the electrons between the atoms that they're bonding with. So using this as an example, so by formal charge counting, this carbon has 5 electrons associated with it, the 2 unshared ones, and half of these 6, which is 3. So one way to easily do this is you just go 1, 2, 3, 4, 5. And the sulfur is the same assignment. Sulfur in this case has 1, 2, 3, 4, 5 electrons assigned to it. Again, the difference here is you split up these shared ones. With octet counting, you do not do that. With formal charge, you do. Now, the formal charge is the difference between the electrons that are assigned in a particular structure and how many electrons an atom of that element usually has. So there are 5 electrons assigned to carbon in the structure. Carbon usually has 4 valence electrons. So it's got 1 extra, so it is said to have a formal charge of -1. Now on the sulfur, normally sulfur usually has 6, or a isolated sulfur atom has 6 valence electrons. The sulfur atom in this molecule, we can assign by formal charge counting 5 to it. It's 1 shy, so it has a formal charge of +1. So the formal charge is the difference in the formal charge electron count of an atom in a particular structure minus what it usually has if it was just an atom by itself. And don't worry, we're going to do plenty of examples. But it is critical to be able to understand the 2 different ways of counting and assigning electrons, because it is fine-tuning formal charge and octets, which tells us, what's a good structure and what's a bad structure. And that is actually the subject of the next couple of videos. See you then.